Hello everyone, welcome to my channel Strong Math. Today in this video we will discuss about some basic definitions of different topics related on set. In the previous video we have discussed about the definition of set and we have given some examples of set. Now today in this video we will discuss about some definitions like subset, superset, universal set, empty set and some basic operations related to set, and they are union of two sets, intersection of two sets, difference and symmetric difference of two sets. So keep watching till the end. So let's start with empty set. Empty set is denoted by phi or second bracket. A set which does not contain any element is called the empty set or null set or void set. So which set is said to be an empty set? The empty set is that set in which no element exists and it is denoted as phi or only second bracket. Often students mistake to write empty set and they write empty set means no elements, no elements means 0. So some students may do mistake and write empty set as 0 in second bracket. But remember, to represent a set we use the second bracket. Now if we write 0 in second brackets, then it is a singleton set. We know that any set consists only one element, then that set is known as singleton set. So if you write 0 in second brackets, then it indicates that set is singleton set, not the empty set. So don't do any mistake to write the empty set. So to represent empty set, use the symbol phi or only the second bracket. Okay, let's look at some examples. The examples of empty sets is number 1, the set of all the boys in a girls school. So is it possible? We know that a girls school means there are only girls students. So the set of all the boys student in a girls schools gives us the empty set. So why empty set? Why? We can't find any number of boys in a girls school. So number of boys in that girls school is 0. So here this set is denoted by phi or only the second bracket. Next, number 2. Let a equals to in second bracket x such that 1 less than x less than 2 and x is natural number. Look, which numbers are natural number? We start from 1, 2, 3, 4 up to infinity. So we know that the natural numbers are 1, 2, 3, 4. So here the set is given as x such that 1 less than x less than 2. Is there any natural number in between 1 and 2? No. So this is also an example of empty set. Now look for the set number 3, b equals to x such that x square equals to 9. So clearly we will get x equals to plus minus 3 as a result. Okay, and 3 is odd number, but here the restriction is given x is even. So this is not possible also. So there is no element in this set also, and hence it is also the empty set phi or the second bracket only. For the set C, x such that x is an even prime number and x is greater than 3. This is also an example of empty set. Why? We know that there is only one even prime number and which is 2. So for x greater than 3 there is no even prime number. Hence this set is also an empty set. Number 5, collection of all negative integers in R plus. You know R plus is a set of all positive real numbers. Positive reals there exist no negative integers in positive real numbers. So this is also an example of empty set. I hope it is clear to you. Moving on to the next section, universal set. Universal set is denoted by capital U. The collection of all sets is called the universal set. It consists all the subsets. We'll discuss later the subset. Then you can understand what is universal set. Just remember, universal set consists all the subsets. Next, finite and infinite set. A set is called finite if it contains finite number of elements. For example, A equals to 0, 1, 2, 3. So number of elements is finite. So A is finite set. Set B, set of all the students of class 11. So the number of students of class 11 are also finite. Hence, these two sets A and B are called finite set. So it is quite obvious that for an infinite set, the number of elements of an infinite set is infinite. For example, set of all naturals is infinite because we know that the natural number starts from 1, 2, 3 up to infinity. So set of all naturals denoted by script n is also infinite set. And for this set, A equals to, in second bracket, x such that 1 less than x less than 2, x belongs to R, real number. We know that number of reals is also infinite. In between 1 and 2 there exist infinitely many real numbers. For example, we can write 1.0001, or you may write 1.00009. So we can't end these numbers. So number of reals in between 1 and 2 is infinite, and hence the set A is also infinite set. Now let's check which of the following sets are finite and which is infinite. Number 1, x such that x belongs to n, set of naturals, and x minus 1 into x minus 2 equals to 0. So if we solve this equation, we will get x equals to 1 and x equals to 2. So this collection gives us as 1 and 2 only. So number of elements is finite, hence this is finite set. For this one, x such that x belongs to n, set of naturals, and x square equals to 4. So we'll get x equals to 2. So the set consists only one element, which is singleton set, and is finite also. For the third one, x such that x belongs to n and 2x minus 1 equals to 0. For this case, we'll get x equals to half. Okay. So what about this set? Can you understand? Okay. So here we have x equals to half, but x belongs to n, set of naturals. Is it possible? No. So here this set is the empty set. So what about empty set? Is it a finite set or infinite set? There is no element in a set which is known as empty set. So this is also finite set. Now what about this set? The last one, x such that x belongs to set of naturals and x is odd. Okay, so let's write the odd numbers, odd natural numbers, 3, 1, 5, 7, etc. As number of naturals is infinite, hence the number of odds is also infinite. So this is an example of infinite set. Now equal set. Two sets x and y are said to be equal if they have exactly the same elements. Suppose the number of elements in x and number of elements in y are equal, as well as the elements are also equal. Then we write x equals to y, which is known as the equality of two sets. If the number of elements and the elements are not same of x and y, then the sets are unequal. For example, suppose a equals to 1 2 3 4 and b equals to x such that x less than 5, x belongs to n set of naturals. This representation, can you remember the representation of set? In the previous video we have discussed the representation of sets. Okay, so this representation is in tabular form and this is in set builder form or method form or property form. Okay, if you have not watched that video, at first watch that video. I have given the link of that video in the I button. So now look, a is 1 2 3 4. What about b? If we write the elements of b, x such that x less than 5, x belongs to natural. So natural number starts from 1 2 3 4 because x is less than 5. So look, a and b are equal sets as the number of elements 4 4 are equal and the elements are also exactly same. So a and b are called equal set and we write a equals to b. Clear? Next, another one. A is the set of prime numbers less than 6. Prime numbers less than 6 means, remember the prime numbers. First prime is 2, then 3, then 5. Okay. Now B is the set of prime factors. Prime factors of 30. So 2, 15 is a 30, 3, 5 is a 15. So collection of prime factors of 30 is the set B and we write B equals to 2, 3 and 5. Now look, the set A is 2, 3, 5 and the set B is also 2, 3, 5. So both are equal. Let's move on the important topic of today's discussion, subset. A set X is said to be a subset of another set Y if every element of X is also an element of Y. That is, the elements of X are also the element of Y. Okay? Then we write X, this symbol Y, and this symbol is known as the symbol of subset. X subset of Y. If small x belongs to capital X, that is small x is an element of capital X, this implies x belongs to Y also, that is small x is also an element of Y. Then x is a subset of Y. If x belongs to X implies x does not belongs to Y, then x is not a subset of Y. This x is not a particular element of X. This should be for all X, and here also this is for all X. Suppose a equals to 1 2, b equals to 2 only. So look, all the elements of b, that is 2, is also an element of A. So we can write B is a subset of A. So for being a subset, all the elements of the first set is also the element of the second set. Every set A is a subset of itself. So A is a subset of A. Phi is a subset of every set. The empty set phi is a subset of every set. Now in the next topic, superset. If X is a subset of Y, that is X subset Y, then Y is called the superset of X. X is subset of Y, then Y is called the superset of X. Proper and improper subset. Let A and B be two sets and A subset of B, and A is not equals to B. A is subset of B and A is not equals to B. Why? Look, in some cases, suppose all the elements of A are also the elements of B. In that case, it may happen that all the elements of A and all the elements of B are equal also. Then they are called equal sets. But by the definition of subset, A is said to be subset of the set B also. So if A is subset of B and A not equals to B, then A is called a proper subset of B. Proper subset of B. That means suppose A have some elements, B has some more elements than A. Okay, this is suppose A. Now look, if A is subset of B, then all the elements of A are also elements of B, but there are some more extra elements in B other than A. So this is the situation in which A is subset of B and A not equals to B, then A is called proper subset of B. For example, A equals to 1, 2, 3, B equals to 1, 2, 3, 4. Look here, all the elements of A, that is 1, 2, 3, are also element of B, but there is an element 4 which is extra in the set B. Okay, so in this case we write A is a proper subset of B, and hence the proper subset is denoted as this symbol. So this is proper subset. Suppose C equals to 2, 3, 1. So basically C and A have same elements. Look, 1, 2, 3, 1, 2, 3. So C is subset of A and A and C are equal also. Then in this case C is subset of A and C is also equals to A, and we write here C subset A. This is called improper subset. Here C is improper subset of A. Okay, because number of elements of because the elements of C and elements of A are equal also. So for proper subset we use this symbol only, and for improper subset we use the symbol of proper subset and a equal sign. Let's discuss some examples. Suppose U, that is universal set, is R, set of real numbers. Now consider the set N, set of naturals, Q, set of rationals, Q complement, set of irrationals, Z, set of integers, Z plus, set of positive integers, and Z minus, set of all negative integers. So look here, this is known as Venn diagram. We will discuss later Venn diagram. Okay, so in Venn diagram we have to write the universal set in rectangular form, and we denote the sets in circular form. So here U, universal set, is R. Now look, suppose this is set of rationals, then this is set of irrationals. Okay, we know that there is no element common in set of rationals and irrational. Rational and irrationals are different sets. So what will be this set? This set will be set of all integers. Okay, what about this set? This is our natural numbers, or we can write also set of all positive integers. Okay, so look, all the natural numbers or positive integers belongs to the set Z. So natural numbers are belongs to the integer set. So set of naturals N is a subset of Z. Very interestingly, look that Q Q complement Z, N, Z plus, Z minus, all belong to the set of real numbers R. So here all the sets, that is N subset of R, Z subset of R, you may write only proper subset, because we know that set of naturals is a proper subset of R. Why? There does not exist all the elements of R in the set N. So this was the concept of subset and superset. We discuss the concept of intervals. Intervals are also subsets of real number. Let a and b be two real numbers and a less than b. The set of real numbers x such that a less than x less than b, strictly less than, is called an open interval, and it is denoted as AB in first bracket. So for all the elements which belongs to this set, that is a less than b, then are also an element of open interval. Look here, a and b are excluded. Okay, so for open interval AB, we write on number line, real number line, that all the elements in between a and b except a and b. So to include the points, we denote this symbol, point included, and to exclude the points, we denote this circle. Next, for closed interval, the set of real numbers x such that a less equals to x less equals to b is called closed interval and is denoted by this, that is in third bracket. So for closed interval, look, the elements in between a and b are also included. So in a real number line, we write the closed interval as included a, included b, and all the elements, all the real numbers in between a and b. So for open interval, we have to exclude the numbers a and b, just we consider the real numbers in between a and b. And for closed interval, we include a, b, and all the real numbers in between a and b. Now look, another one, half open half closed intervals. They are like, in the left hand side the interval is open and in the right hand side the interval is closed, or the interval is closed in the left hand side and open in the right hand side. So for this case, we write open at a, that means the point a excluded, and closed in b, that is the point b included in that interval, and all the points in between a and b. Okay, for this type of interval, closed at a, that means the point a is included and the point b is excluded, and all the real numbers between a and b. So the definition of half open and half closed interval is, for this type of interval, open a closed b, that is x such that a less than x less equals to b, and closed a open b means x such that a less equals to x less than b. Remember one thing, an interval of real numbers consists infinite number of elements, because we know that for any two consecutive reals a and b, there exist infinitely many elements in between them. So number of elements in an interval is infinite. Let's discuss another important topic, which is known as power set of two sets. The collection of all possible subsets formed by the elements of a given set A is called the power set of A and is denoted by P of A. What happened? All the possible subsets formed by the elements of a given set A. Suppose A is given 1, 2, 3. Now the elements of A are 1, 2, 3. the set formed by the elements of A is called power set of A and is denoted by P of A. Let's discuss how to form power set. Look, there are three elements in A. How to make subsets of A? Look, if we take no elements of A, that is phi is also a subset of A, because we know that phi is subset of every set A. Okay, so if we take no elements of A, then we will get a subset of A which is known as phi. So phi is subset of A. So this set is formed by taking no elements of A, by taking no elements of A. Now look, if we take one element from this set, then we will get singleton 1, singleton 2, singleton 3. So these three are also subsets of A. Okay, and they are formed by taking one element of A. Now look, if we take two elements from A, then 1 2, 1 3, 2 3, they also form a subset of this set A. So taking two elements of A. Now if we take the three elements, that is all the elements of A, then we will get 1 2 3. This is also a subset of A, and here taking three elements of A. These are all the possible subsets of A, that is taking no element, taking one element, taking two elements, and taking three elements, and maximum number of elements of A is 3. So the collection of these sets by definition of power set is power set and is denoted by P of A. So P of A is the collection of all possible subsets formed by the elements of A, and the power set of A is phi 1 2 3, 1 2 1 3, 2 3, and 1 2 3. Similarly, let's discuss another example. Suppose B equals to 1 and 2. In the same process, if we take no elements of B, then phi one element 1 2, two elements 1 and 2. So the power set of B denoted by P of B is phi 1 2, 1 and 2. Now Venn diagram. To draw a Venn diagram, we have to draw a rectangle, which is the notation of universal set, and the sets are represented by circle. Most of the relationships between sets can be represented by Venn diagram. Now look, suppose a set A consists 1 2 3 elements, and universal set is the set of real numbers. Okay, so set of real numbers being the universal set, we have negative integers negative 3, negative 2, 0, negative 1, etc. Then 1 2 3, but 1 2 3 are also the elements of A, set A, and this is set A. So we have to write 1 2 3 in the circular region, because 1 2 3 are also the elements of A as well as U, that is R. Next 4 5 6 up to infinity. So look, A, all the elements of A are also element of U, set of real numbers. So we write A is subset of the universal set. Okay, another example, suppose A equals to 1 2 3. Okay, and U equals to 1 2 3 4 5. So look, For 1 to 3 we have to write 1 to 3 in the circle A. So 1 2 3, 1 to 3 are written. Then 4 and 5 will remain outside the set A. So suppose here 4, here 5. So this is the representation of sets in Venn diagram. Let's discuss the final section of this discussion. Operations on set. Operations on sets means for two numbers we can operate in between them. Suppose there are 2 3, we can add them 2 plus 3, we can subtract them 2 minus 3, we can product them 2 into 3, we can divide them 2 divide 3. So for two sets there are some operations. Number 1, union of two sets. The union of two sets A and B is denoted by A union B. This is the symbol of union and is defined as, suppose X belongs to A union B, then we will get X is belongs to A or X belongs to B. This is the definition of union. Okay. As A and B are two sets, then A union B will also be a set. So definition of A union B is X belongs to A union B implies X belongs to either A or X belongs to either B. So remember, for union we have to write OR. Now in Venn diagram, suppose this is set A, this is set B, and this set is known as universal set U, then A union B will gives us the set marked by the red pen. Okay, so this is A union B. Number 2, intersection of two sets. The intersection of two sets A and B is denoted by A intersection B. This is the symbol of intersection and is defined as X belongs to A intersection B implies X belongs to A and X belongs to B. For intersection we have to write the word AND. For Venn diagram, A intersection B means, look, X belongs to A intersection B means X is an element of A and X is an element of B also. That is, X belongs to the common portion of A and B. For Venn diagram, look, this portion is common and A intersection B means the common region which is marked by red ink. Number 3, difference of sets. The difference of two sets A and B is denoted by A minus B and is defined as, if X belongs to A minus B, this implies X belongs to A but X does not belongs to B. Don't mistake, A minus B means the difference between the set A and B, not the difference between the elements. Okay, so don't subtract the elements from the set A to the set B. Okay, A minus B means X belongs to A but X does not belongs to B. Look at the Venn diagram. This is A set, this is set B and this is the universal set. Okay, so A minus B means the elements belongs to A. All the elements belongs to A but not belongs to B. Look, this element is in common of the set A as well as B. So these elements are also present in B as well as A. So we have to mark the elements which belongs to A only but not B. So this is A minus B. Finally, symmetric difference. A symbol of delta, B. This is the symbol of symmetric difference. Asymmetric difference B means asymmetric difference B is equals to A minus B union B minus A. So the union of A minus B and B minus A gives us the symmetric difference. That is, A minus B is a set and this is B minus A. Their union gives us a symmetric difference B. Let's discuss some important and obvious properties of sets related to the operations. First one, A union B equals to B union A. A intersection B equals to B intersection A. These two properties are known as commutative law for union as well as intersection. Now what about the difference? A minus B and B minus A are equal. Look, suppose this is set A, this is set B. Now A minus B means this set, this is A minus B. B minus A means this set, this is B minus A. Are they equal? No, they are not equal. So for this difference, A minus B is not equals to B minus A. So commutative law does not hold for difference. Next, associative law. A union B union C is equals to A union B union C. A intersection B intersection C is equals to A intersection B intersection C. Both are known as associative law for the union as well as intersection. Next, A union A gives us A, and A intersection A is A. Common of A and A is also A, and collection of A and A is A. This is known as idempotent law. Now, A union phi, A union nothing is A. A intersection phi, A intersection nothing means nothing. Why? Because we know that phi is also an element of A. A union U, that means A union universal set, the universal set, and A intersection universal set, common portion of A and universal set is A. Now look, let's explain the distributive law. A union B intersection C is equals to A union B intersection A union C. Here union is distributed over intersection. Look, A union B intersection A union C. Similarly for intersection over union, A intersection B union A intersection C. How to remember? Suppose you have x into y plus z. For numbers we write xy plus xz. Now what will happen for difference? Suppose A minus B union C. Okay, which one is correct? A minus B union A minus C or A minus B intersection A minus C? Suppose this is set A, this is set B, this is set C, and this is set U. A minus B union C. B union C means B union C means this set. Okay, now A minus B union C means this is A minus B union C. Okay, this is A minus B union C. Now here A minus B union C is equals to the dotted line. So to get this dotted line, we have to take the intersection of the blue color and the green color, then we will get this one. So for A minus B union C, A minus B intersection A minus C is the right answer. Let's end our today's discussion by giving a definition of disjoint sets. Two sets are said to be disjoint if there is no element in common. That is, if A intersection B equals to phi, then A and B are called disjoint sets. In Venn diagram, look, this is universal set, this is set A, this is set B. Is there any element in between A and B? No. So here A intersection B is equals to phi, and hence A and B are called disjoint sets. This was the basic concept of sets and basic concept of the operations on sets. If there is any kind of doubt, then comment below and keep watching Strong Math. Thanks for watching this video. Please like, share and comment, and obviously please do subscribe my channel Strong Math. Mention your query. Keep watching. Thank you.